So we've got the output so far of the convolutional part of our convolutional neural network, which is a 3 by 3 by 64. Commonly then what happens at the end is we go ahead and have one or two fully connected layers. So we're going to go ahead and take this. In order to do a fully connected layer, we're going to have to actually flatten this. So flattening this is going to take us now into something of size 3 by 3 by 64. So we can do two fully connected layers here. Let's say we can go from 3 by 3 by 64 to let's say something of size 64. And then we can go ahead and feed this into something of size 10. So again, fully connected layer here, fully connected layer here, and then our output we can dig out into a softmax. So that's not uncommon to have convolutional neural networks where the first part of the convolutional neural network is a set of convolutions, right? Convolutions, ReLUs, and pooling, until eventually we get kind of to the end of the convolutions, and then we say, okay, let's just switch over to one or two layers of fully connected. So we flatten it and then go into fully connected. There is an alternative, however, which lets us stay within convolutional land. Let's say we have our 3 by 3 by 64, and then we go ahead and apply convolutions to these, 3 by 3 convolutions. In fact, let's say we have 64 of them. Well, let's just look at what would we end up with. We would end up with each one of these convolutions would apply to this entire 3 by 3 by 64 and would yield us one output. So we would have a 1 by 1, and we would have, because of the 64 kernels, 64 of them. Let's look at the first value here. So this first value right here, I claim is the same as this value here. This value here is getting calculated by taking a weight, right? Different weights times every one of these 3 by 3 by 64 values. This value here is getting calculated by taking each of these 3 by 3 by 64 values and multiplying them by a weight. And in both cases, of course, we had a bias as well. So we're calculating exactly the same thing here as we are here. And then we're doing the same thing for each of the other 63 entries. It's just arranged sort of differently, right? This one is arranged flat with a matrix here. Here, we've actually, so a two-dimensional matrix for our weight matrix. Here, we've got a three-dimensional convolution holding the same weights, though. And then we could go ahead and apply here. So this is a convolution. We could apply another convolution. So the next convolution we're going to do is we're going to do a 1 by 1 by 64. And we're going to have 10 kernels. So the output of this is going to be a 1 by 1 by 10, exactly equal to here, right? Same number of values. The only difference is this is three-dimensional and this is one-dimensional. And at this point then, we can leave convolution land, do a flat, and then just get ourselves a vector of size 10 that we can then do our softmax on. So this is just an idea of how you can stay using convolutions all the way sort of to the bitter end of your convolutional neural network. And only flatten at the very last instant, where basically you're just getting rid of these 1 by 1 dimensions here.